Okay. So, Andre, you talked about mostly about states of consciousness, and I'm only going to talk about consciousness of contents, namely being conscious of some stuff or unconscious of some stuff. All right. So I'm going to explain what the criterion problem is. I'm going to explain how to solve it. Then I'm going to present a new criterion problem. I'm going to show how we can solve it too. And so my conclusion will be that if we are smart enough, if we are inventive, consciousness scientists can solve these problems and find ways of assessing what people consciously experience. So that will be a kind of counterpoint to what Andre said in the case of states of consciousness. All right, so of course you cannot discover anything or test any hypothesis about a phenomenon if you're unable to identify when that phenomenon occurs and when it doesn't. That's true for everything. If you want to learn more about photosynthesis in plants, you have to be able to determine whether photosynthesis occurs or not. If you want to learn more about volcanoes, you need to determine what counts as a volcano and what doesn't count as a volcano. And if you want to study consciousness, you need to be able to determine when people are conscious of some stuff and when they are not conscious of some stuff. Okay, so in consciousness science, we need to be able to determine when subjects consciously perceive stimuli that we show them, when they unconsciously perceive them, and when they don't perceive them. So there's a difference between unconsciously perceiving something and not perceiving something. Yes, Johan.
Sorry, this was from the previous. I forgot to take it away. Sorry, from the previous talk. I'll take it away.
Okay.
Sorry.
Okay. So in a nutshell, we just need consciousness detection procedures. So these procedures are procedures to reliably determine whether subjects consciously perceive stimuli, unconsciously perceive stimuli, or don't perceive stimuli. So I'm not going to say a lot about those procedures themselves. I'm just going to assume that the best procedures that we have right now rely on so-called subjective reports, which can come under various forms like confidence ratings, perceptual awareness scale ratings, or visibility ratings. That is, just assess the visibility of the stuff you're shown. In general, these reports in consciousness science are obtained after a type 1 task. So a type 1 task could be a discrimination task. You're shown something that goes very, very fast. It's masked. And then you have to say whether the stimulus was a square or a diamond, for example. And then you have the type 2 task in which you're asked whether you saw the stimulus or not. Now, what consciousness scientists generally do, it's a bit more complicated than that, but the basic idea is that you're going to conclude that there's unconscious perception when people can do the type 1 task above chance, which indicates that they see the stimulus, and their performance on the type 2 task is at chance, or they say that they don't see the stimulus. Okay, so if you have evidence that I see something, but I report not seeing it, then that means that I unconsciously perceive it. That's the basic idea. Now, before we go further and see what the problem is with this, I'm going to say a few things about signal detection theory, which is the main framework that we use in order to understand how subjects provide these seen versus not seen reports. So the basic idea in signal detection theory is that people report seeing the stimulus if stimulus strength falls above a criterion for reporting the stimulus as seen. Okay, if the signal is strong enough, you're going to report seeing the stimulus because it falls above your response criterion. On the other hand, you answer not seen when the strength of sensory signals remains below this threshold or this criterion for answering seen. Now, ideally, people would respond that the stimulus is present only when, given the sensory evidence they have, the probability that the stimulus is present is higher than the probability that the stimulus is absent. But unfortunately, people can be biased. Some people don't need a lot of sensory evidence before they answer seeing the stimulus. They have a liberal bias, they are liberal observers, and other participants need a lot of sensory evidence. It's like they don't really want to say that they see the stimuli, and so they have a conservative bias. It will need a lot of sensory evidence for them to say that they see the stimuli. Now, it turns out that people working on signal detection theory have often observed that as perceptual sensitivity goes down, so that's measured by D prime here, which measures basically the distance between those two distributions. If you suck at the task, if you're bad at the task, you're going to become more conservative. That's just something that people have observed over the years. And that's called the Niemann-Pearson objective. Basically, when people do these tasks, if they become worse at the task, they also become more conservative. That's because implicitly people have the goal of minimizing the number of false alarms, namely saying that they see the stimulus when the stimulus was not present. So that's the Niemann-Pearson objective. And that's a big problem. That's a big problem in consciousness science, because in order to make the stimuli unconscious, what do? Well, we make people bad at the task, basically. That's what we do. For example, we are going to mask the stimulus with a visual mask, and so people will not be as good at identifying the stimulus. And so when we do that, what we do is also that we make people more conservative because of the Niemann-Pearson objective. So now let's come back to this simple example. We've seen that some participants will have a tendency to answer that they don't see anything. These are the conservative observers. And other participants will say that they see the stuff almost all the time. They are the liberal observers. Now, because of the Niemann-Pearson objective that I've just described, we have reasons to believe that most people in consciousness research, when they do consciousness research experiments, they are like this guy. So they have a conservative bias. And conservative biases raise a huge problem called the criterion problem. And the problem is this. There are now two interpretations of what the not seen reports really mean with respect to the subject's consciousness of the stimulus. So you show them the stimulus, it's masked, and they say they don't see the stuff. But now we are not sure about what the not seen reports really mean. The first interpretation is very simple. It's that she didn't see the stimulus. That's what not seen means. So that's a straightforward interpretation. But now we have another interpretation. The other interpretation is that she saw the stimulus consciously, but stimulus strength fell below her conservative criterion for answering C. So she saw it consciously, but because of her conservative criterion, she answered that she doesn't see the stimulus. So that's the criterion problem. How are we going to determine which of those two interpretations is right? Okay, and you know, that seems like a tough problem to solve. And the reason why that seems like a difficult problem is that how could we know whether the participants answer that they don't see the stimuli because they don't see the stimuli, or because they have a tendency to respond that they don't see the stimuli? It seems like, you know, people would say the same thing in both cases, right? So how would we know? How would we know? And it seems like an impossible problem to solve, but it's possible to solve if you're inventive. So that's going to be my general point here. And it was actually solved by Megan Peters and Hakwan Lau in 2015. And they designed this very smart task. So in this task, subjects were presented with a target, which could be either a left-tilted grating or a right-tilted grating. And this target was embedded in a stream of masks. So it goes like this: mask, 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 target, mask, 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 mask. So because it's embedded in this stream of masks, you don't see the target very well, okay? And your task is, you're presented the target, you have to say whether it's tilted left or right. So that's the type 1 task. Then you're told you're told that you're presented with the target a second time, and you have to say whether it's left or right. And then you're asked on which of your two decisions will you bet on. Or in a control experiment, they asked in which interval was the stimulus more visible? Was it more visible the first time we showed it to you, or the second time? Was it more visible the first time or the second time? Of course, if you do this task, in your head, you're thinking that the stimulus was presented each time, right? You don't know that, in fact, one of those two intervals is always empty. In one of each, sometimes, very often actually, you do this task and it's actually impossible to do it because there's nothing, you're shown nothing. Okay. And the idea is this: if you see the stimulus unconsciously, seeing a stimulus feels just like not seeing it. That's what seeing something unconsciously feels like, right? Seeing something unconsciously feels like not seeing the thing. So if you see this target unconsciously, you should judge the target to be as visible as no target, right? You should judge the target to be just as visible as nothing. That's what unconscious perception feels like. So if the subjects see the stimuli unconsciously, they shouldn't be more confident in their decisions when the target is present compared to the target is absent, and they shouldn't judge the target to be more visible when it's present compared to when it's absent. Okay, so here is the idea. You do the task in the first interval, in the second interval, and then you're asked in which interval was the stimulus more visible. Okay, and if you're above chance on the discrimination task, that is on saying that the target is left tilted or right tilted, I'm going to conclude that you saw the stimulus because that's the explanation for your performance. But if you're at the level of chance for answering whether the target was more visible in this one than this one, I'm going to say that you are not conscious of the stimulus. So I can assess unconscious perception in this way. Now, here's how it solves the criterion problem. Let's imagine that you're a conservative observer. What would your conservative criterion lead you to answer? Well, nothing in particular, because there's no reason to think that your conservative bias should lead you to prefer somehow answering first interval versus second interval. Okay? Here, we are not asking you whether you saw the stimulus or not. We're asking you in which of those two intervals the stimulus was more visible. It's a comparative question. So your bias doesn't apply here. So that's how we can solve the criterion problem, by using these tasks that are bias-free. Okay, so here's what we would expect if there is some amount of unconscious perception. We would expect that participants can do the discrimination task, they can tell you whether it's left or right, and yet they're unable to tell you that the target was more visible in the target present interval compared to the target absent interval. Okay, so we should find this kind of hockey stick in the data. And what's embarrassing is that when we do this task, we don't find that. We don't find that at all. So when we do the task and participants are not biased, there's no unconscious perception. Okay. So that's embarrassing. That's embarrassing because it means that it suggests that in all the other cases where we thought there was some unconscious perception, actually maybe there was no unconscious perception. So that's bad. So there are several reasons to think that their experiment underestimates unconscious perception. I've published some articles on that recently, but let's talk about that later. For now, the crucial point is just that we can develop these non-biased tasks in order to objectively assess unconscious perception. Okay, so the good news is that we can solve the criterion problem. The bad news is that the only paradigms that solve it have not found evidence for unconscious perception yet. And the second bad news is that there's a new criterion problem. So to understand the new criterion problem, I have to explain a few things about the interpretation of the criterion measure in signal detection theory. So remember, the criterion is the stuff you're moving around that doesn't seem to correspond to what you actually experience. So a common interpretation in signal detection theory is that D prime measures your perceptual sensitivity, and it indicates the quality of your perception. C, on the other hand, which is the criterion measure, indicates a cognitive factor determining your decision to answer. Okay, so that corresponds to your report, that corresponds to what you see. And you find this interpretation in classic textbooks. If you have studied signal detection theory, that's probably what you've been told. So here's what Green and Sweats say. Modern detection theory shows how to compress a host of factors which affect the observer's attitude into a single variable called the decision or response criterion by extracting two parameters from the data, one related to attitude and one to sensitivity. The procedures of detection theory isolate non-sensory factors so that a relatively pure measure of sensitivity remains. Okay, so that's a very common interpretation. And the consequence of this is that, let's say that I have a manipulation, an experimental manipulation, like I zap your brain or I do something. And this manipulation changes C without changing D prime. The inference that most people will draw is that that manipulation changed your tendency to respond, but not your actual experience. Okay, that's the inference that most scientists will draw based on this. Okay, so that's the idea. But that's the wrong interpretation of the criterion measure, even though it's quite popular. So to understand why, I'm going to use an example from Jessica Witt and colleagues. So let's say that your task is to discriminate between short lines and long lines. You can show that the distributions here will represent the space between those two distributions will represent how similar those lines look to you. If you're completely unable to discriminate between the two, it means that the lines look identical to you, and so your two distributions will overlap. If the lines look very different to you, the two distributions will be very far. Okay, so let's say that you put your response criterion in the middle here, such that when you perceive the lines as being, let's say, less than 5 centimeters, you answer that the lines are short, and when you perceive the lines as being more than 5 centimeters, you answer that the lines are long. Now, let's imagine that I give you a lot of money in order to answer that the lines are short. You'll move your criterion such that you will now answer short more often, right? Because you want to earn a lot of money. So basically, by giving you a lot of money, what I'll do is that I will shift your criterion and you will answer short. Of course, my giving you a lot of money doesn't change what you see, okay? So the change that I'm inducing here will shift your response criterion, but it will not change your perception, okay? It will not change your perception. Now, let's imagine something different. Let's imagine that instead of giving you a lot of money, I do this. I put inward arrows at the end of each line, such that I create the Muller layer illusion. All the lines are now perceived as being shorter. So the short lines are perceived as being shorter. So those two lines are actually the same size. But the long lines are also perceived as being shorter. So those two lines are the same size. So what will happen in this case? What will happen in this case? Well, now the response distributions for short and long lines will shift to the left. They will shift to the left because now you perceive all the lines as being shorter. But look at what happens if you don't move your response criterion as a result. If you don't move your response criterion, now you will answer more often that the lines are short. Okay? You'll answer more often that the lines are short. So that's a case in which a perceptual effect leads to a change in your tendency to report that the lines are short. So now we have these two cases. In one case, there's a perceptual bias. In the other case, there's a response bias. And the problem is that the criterion measure in both cases is the same. It's the same. Okay? So the criterion measure does not distinguish between response bias and perceptual bias. does not distinguish between response bias and perceptual bias. And basically the idea is that the same thing could apply to other cases. Let's say that I manipulate your brain activity in the back of your head by zapping your brain. And now you have a tendency to answer. I do signal detection theory, and I show that you have a tendency to be more conservative. That is, you answer not seeing. There are now two interpretations. Did my manipulation manipulate your response criterion in order to create a response bias? That is, my manipulation changed your tendency to respond that you don't see the stimulus? Or did my manipulation caused a perceptual bias? Namely, did my manipulation change your tendency to actually see the stimulus? Okay. So we have those two interpretations, and distinguishing between those two is the new criterion problem. So the new criterion problem is that changes in the criterion measure in your tendency to respond to something could be interpreted either as indicating perceptual effects, as in the case of the Müller-Lyer illusion, or post-perceptual decision strategy changes in your tendency to respond that the stimulus is present. And again, how could we ever know which of those two interpretations is right? Again, it seems like whichever interpretation is right, people would report the same thing. Right? So that's a problem again. So in order to show how we can solve that apparently unsolvable problem, I'm going to take a case study, an experiment by Yemi and Bush. So there's evidence in the empirical literature by Benwell and colleagues in 2017 and by Jason Samaha and colleagues in 2017 too, that if you have high pre-stimulus excitability in the back of your head, which is indexed by weak alpha and beta power, the EEG signal, people will tend to give high visibility ratings, and they will have a more liberal detection criterion. So if you show them some stuff, they'll tend to say that the stuff is present. Now, we've seen that we could have two interpretations of this. One hypothesis is that high pre-stimulus excitability will change your tendency to respond that the stuff is present or that it's more visible. A different hypothesis is that it will change your tendency to perceive the stimulus. Okay, so in one case, high pre-stimulus excitability causes a perceptual bias. In the other case, it's a post-perceptual bias. And we don't know which one is right. So again, we can come back to this illustration. It's possible that high pre-stimulus excitability shifts your criterion. That's a response bias. But it could be that high pre-stimulus excitability shifts the distribution, and it's a perceptual bias in that case. And so we are trying to determine which hypothesis is true now. Again, it seems like a difficult problem to solve, because how could we know whether it leads to an increased visibility or to an increased tendency to report higher visibility? So the bad news, again, is that there's no systematic solution to this problem. And the good news is that we can probably solve it, but on a case-by-case basis by being inventive. So here's how we solve it in this particular case. It can be solved if we note a crucial distinction between 2IFC detection tasks and 2IFC discrimination tasks. So in a 2IFC detection task, I present you a stimulus, a target, which could be a left or right tilted grating. And in the other interval, there's nothing. And I ask you in which interval the target was present, the first interval or the second interval. In a discrimination task, I'm going to present you a target, which in this case is a left tilted grating, as here. But in the other interval, it's not going to be empty. There's going to be a right left tilted grating. And I ask you, was the target present in the first or second interval? So you can see that those two tasks are super similar, but one case it's discrimination. You ask to discriminate between left tilted and right tilted. In the other, you're just detecting this stuff. Okay, according to signal detection theory, here's how you do this task. You have one feature detector one detector in your head that I represent here as a little robot. In my head, it's like I have a little robot that tells me when the target is present. And so it will screen target. And in the target present interval, it will say target, but it will not say that as much. My little robot will not be as excited. And what I can do to solve this task is just compare the activity of my little robot in one case to what happened in the other case and say that the target was present when my little robot was more activated. And that's how I solve the task. In a 2IFC discrimination task, I don't have one little robot, but I have two robots because I have two feature detectors. And signal detection theory says that I solve the task in this way. My left tilt robot will say left tilt, my right tilt robot will say right tilt, and what I'm going to get at the end of the day is a balance of evidence between the strength of the signal given by my left tilt robot and my right tilt robot. So let's say that in that case, I have 80% evidence for left tilt. In the other case, in this interval, that's not the target, so that my right tilt robot will be much stronger, and I'll get only 10% evidence for left tilt. And the way I can do this task is just compare the relative evidence for left tilt in those two intervals and answer with the interval with the highest relative evidence. That's how signal detection theory says you solve this task. Okay, now let's come back to our pre-stimulus excitability stuff. Let's imagine that I have a perceptual bias. And the way we would model a perceptual bias is basically as boosting the activity of your target detectors. A perceptual bias in that case will boost the activity of your target detector. So now the target, my robot will be so excited by this perceptual bias. So it will say target even more. And so if you have high pre-stimulus excitability, here what will happen is that you will increase the activity of my target detector. And so ultimately what will happen is that you will have an increased hit rate. That is, you'll be better because now the balance of evidence is even higher in favor of the target present interval. Okay. Now let's imagine what happens in the case in which you have a response bias. A response bias will lead you, a response bias before this interval will lead you to answer with whichever interval had the highest level of pre-stimulus excitability. So in that case, you'll have a response bias to answer first interval. Note here that the activity of your detector does not change because it's a purely response bias. It does not affect your perceptual detectors. You just have a tendency to answer that the target was present in whichever interval had higher pre-stimulus excitability. In that case, the first interval. So in that case too, that will lead to an increased hit rate. So as you can see, it seems like a detection task cannot solve the problem because in both cases, what we predict is that we'll have a higher hit rate. Namely, people will be better at answering where the target is. But now, in the discrimination task, remember what we have. We have two feature detectors. And what happens is that we get the balance of evidence between the two. Now, let's imagine that you have a perceptual bias. A perceptual bias, again, will boost your feature detectors. So you'll get more evidence for left tilt, but you'll also get more evidence for right tilt. And so ultimately what will happen, and that's very important, what will happen is that the balance of evidence will be the same. Because now you have more evidence for your little robot for left tilt is more excited, but your little robot for right tilt is also more excited. And so on balance, it will not change. And so that doesn't change the hit rate because the proportion of evidence you get for left tilt versus right tilt does not change. Now, let's imagine what happens in a case in which you have a response bias. If you have a response bias, you'll have a tendency to answer with whichever interval had higher pre-stimulus excitability. And in that case, that means that you have a higher tendency to answer that the target was present in the first interval And in that case, that will increase your hit rate. So we have a difference between the two hypotheses. If you have a perceptual bias, the prediction, if you have a perceptual bias, will be that there's no difference between high and low pre-stimulus excitability in the discrimination task, since the relative activation of your two detectors will, at the end of the day, be the same. If high pre-stimulus excitability leads to a response bias, namely a tendency to answer that the target was present in the target present interval, this will lead to an increased hit rate when pre-stimulus excitability is high in the target present interval. And so you'll be better at the task. And what they found was this, that high pre-stimulus excitability indicated by weak alpha and beta power, before the stimulus is presented, that doesn't increase your performance. But still, you say that the stimulus is more visible. Okay, that doesn't increase your performance on the discrimination task, but you still say that the stimulus is more visible. And so we can conclude from that that high pre-stimulus excitability does change your perception, not just your tendency to report that the stimulus is visible. So again, high pre-stimulus excitability changes what subjects perceive, not just their perceptual judgments or their tendency to respond that the target present, that the target is present or more visible. So this shows that the new criterion problem can be solved. Okay, so here is my conclusion. The criterion problem and the new criterion problem both come from the same source. The problem in each case seems to be, how can we identify whether an experimental manipulation, like manipulating, for example, stimulus excitability or masking the stimulus, how can we know whether that manipulation changes what people see or what they report seeing? And it seems like a tough problem again, because how would we know? Because people would give the same reports in both cases, right? And again, that seems like a difficult problem to solve, you might think. How could we know subjects would report the same thing in both cases? But I think if we are inventive enough, we can solve these problems that seem prima facie really difficult to solve, and find ways of determining whether our experimental manipulations change what people consciously perceive or just what they report perceiving. Okay, so that's an optimistic conclusion for consciousness research. Thanks.